Here we go. All right, so 3 states of matter: gas, liquid, solid. So we'll talk about gases completely. There's a whole section on gas laws and kinetic molecular theory and all that stuff. Liquids and solids we'll talk about in terms of intermolecular force. We'll also have phase diagrams that we'll talk about all within this unit. That's why this unit is going to be a while. All right, so intermolecular forces. What is intermolecular mean? It means it is between molecules. Okay, so we're talking about how do molecules, how are they held together? So if we're talking about solids, right, we know that solids are structurally all kind of nice and compact, but what holds them in place has to do with what kind of attraction is between them. Now, all intermolecular forces are weak, but some are stronger than others. So this is nothing like a bond, right? A bond really takes a lot of energy. Remember last unit we talked about, in order to form a covalent bond, you have a certain amount of potential energy, right? Molecules have to come closer together and so on and so on. But with this, it's just a force of attraction. And that force of attraction, no matter what kind it is, it's a weak force of attraction. But in the case of hydrogen bonding, because there are so many of them within water molecules, it actually makes it really strong. Like water has really high surface tension, right? Water takes a lot of energy to boil. All that is because of this really weak force, which is the intermolecular force. And you can see in this diagram right here that that's H bonding. It's not a bond. Once again, H bonding has nothing to do with a bond. It is a force of attraction between the hydrogen that's bonded to an electronegative, attracted to another electronegative element that has a partial charge. Yes?
In the red down there, it says intramolecular. Is there a difference between that and intermolecular?
So intramolecular is bond. Covalent bond, ionic bond, metallic bond, that is an intramolecular force. Intermolecular is H bonding, London dispersion, van der Waals, and ion dipole. Okay?
So
and dipole.
The bond between atoms is stronger than the bond or the force between molecules? Or is it the opposite?
Yes. The bonds, covalent bond, ionic and metallic, that holds a compound together, right? So let's say we have NaCl that is held together, the sodium and the chloride is held together by ionic bond. That is very, very strong compared to a dipole-dipole. Does that make sense?
Yeah.
Yeah. All right, so intermolecular forces as a group, we call them van der Waals forces, but we split them into different ones depending on what kind it is. So we're going to talk about H bonding, we're going to talk about London dispersion, dipole-dipole, and ion dipole. Okay, so but all of them together can be referred to as van der Waals forces. So if you hear that term, you know that we're talking about intermolecular forces. Okay? So far, so good? Yeah.
Okay.
Oh, okay. Yeah. Okay. So here are the three that we're going to concentrate on. Dipole-dipole. So that's between two molecules that have a dipole moment. Hydrogen bonding, that obviously involves a hydrogen. And London dispersion, which has to do with a non-polar compound. So London dispersion is also considered momentary, temporary dipole. So for whatever reason, sometimes the valence electrons or the electrons within a bond shift more to one side than the other, and that creates a momentary and temporary dipole. Okay, so we call it a dipole, but it's not. So London dispersion is really just a very temporary, short-lived dipole that happens in a compound and then goes. Okay, that's what holds it together. So the more elements a compound has, in other words, the bigger the compound, the more electrons there are, the more possibilities for London dispersion forces. In the case of hydrogen bonding, you need to have a hydrogen bonded to an electronegative element. You have to have that partial charge. In the case of dipole, that's that electronegativity difference, right? If you have a polar bond within a compound, you're going to have some, again, partial charges that are going to get attracted to another compound similar. Hydrogen bonding is really just an example of a dipole. It is a specific type of dipole involving hydrogen. Okay? And then the fourth kind of intermolecular one, the one I was telling you, is ion dipole. In this case, you have to have one ion, so there's an ionic compound. Let's say sodium chloride dissolves in water, right? When sodium chloride dissolves in water, what makes it so soluble is the fact that sodium separates from the chloride and is surrounded by water molecules. Now, what I want you to think of is separate sodium and chloride as ions. I want you to draw this out. I want to see the molecular drawing. So separate sodium and chloride and tell me how the water would surround each ion. So think about this. Sodium is what is the charge of sodium? What's the charge of sodium?
+1.
All right, what's the charge of chloride? -1. It has 7 valence. It's going to be -1. Okay, now, how would the water molecules surround the sodium?
The oxygens would face towards the sodium.
Yeah, so the oxygens would face the sodium, right? How would the water molecules surround the chloride? The hydrogens would face, right? So something like that. Now, so the interaction between that oxygen end of the water molecule and sodium, the hydrogen end of the water molecule and chloride, that's ion dipole interaction. That's what makes an ionic compound so very soluble in water. The fact that it can separate the ions and surround them so that you have max amount of attractive forces between them. Okay? Questions? And by the way, that's what happens. This is why when you add salt to water, it increases the boiling temperature. Okay? So it takes longer to boil water that has salt in it, but it will boil at a higher temperature than 100 degrees Celsius. But it will take longer because you have all these ions all the ions and water molecule interactions that takes more energy to actually break. Okay? All right, so let's start with dipole-dipole interaction. So you have to have dipole within the compound in order for this to happen. And if it's a dipole, that means there's a polar bond, right? And the polar bond causes partial charges. Remember we talked about the partial positive to one side and partial negative to the other. And of course, when that happens, you're going to have attractive forces between the positive and the negative and positive, right? And molecules that have these permanent dipoles are attracted to each other, and these are as strong, almost as strong as the H bonding. So when you look at the strength, dipole and H bonding are really similar in strength because they're really the same kind of interaction. It's between a partial positive and a partial negative. Okay, so partial positive, because again, what causes this partial positive, partial negative, remember, is a difference in electronegativity. Okay, so that is a polar bond. Polar compounds are attracted to each other with dipole-dipole because of that pull and because of the partial charges. Okay, questions? Okay. Yeah. So, if we're talking about a polar molecule like carbon bonded to chlorine or something like that, right? All those bonds, even if the entire molecule is not polar, by the way, remember the bonds have a dipole. And that pull is enough to attract another molecule. Yeah.
Do they have dipoles if it's like a perfectly like non-electronegative If you have like
If you have a symmetrical compound that is not a polar compound, right? So for example, if we have carbon tetrafluoride, the compound overall is not polar. However, are the bonds polar? So then the bonds have a dipole if they're polar.
if it's
Yes.
like, if it's like H2,
Then no.
no.
Good morning, Dean Toledo. I hope you all are having a great week. Today's college visits are to Emerson College, Skidmore College, Seattle University, and IDCS Fishham. Today's Torah reading minyan is at bonus, and Leonard minyan is from 3:20 to 3:35, both in room 180. Lastly, we want to wish a good luck to our 10th girls tennis team and our flag football team. Have an amazing day.
All right. So if a bond is non-polar, right, like you said in the case of two hydrogen atoms, would it still have some kind of intermolecular force? Yes. It wouldn't be dipole-dipole. It would be London dispersion forces, which we'll talk about in a minute.
So London dispersion forces would be for,
Non-polar compounds.
but so does that mean all of the where it's like what is it called where it's just two of those molecules bonded together?
Like the same molecules? Like the binary compound, the binary ones?
binary.
Yeah. All right. So the more polar, the higher the boiling point, as you can see here. So what makes, so you get a lot of questions like this on the AP where they give you data and you have to justify given the data. Now, when you look at this, propane has a boiling point of 231 compared to acetonitrile that has a boiling point of 355. Whenever you're dealing with this kind of question where it's boiling point and all that, usually it has to do with an intermolecular force. Okay, so what causes something to boil is to break the intermolecular forces between them to turn into gaseous compounds, right? So if you had to justify acetonitrile's boiling point compared to propane, what would you say? So if the question said, why is it that acetonitrile, even though it has less number of carbons, less number of hydrogens, has a much greater boiling point than propane, what would your answer to that question be? Yes?
It has more dipoles.
So because it has a polar bond, do you see any polar bonds in propane? No. So when you have non-polar bonds, the only kind of intermolecular force you have is London dispersion. London dispersion is induced and temporary. So it's a very short-lived one. Whereas when you have an electronegative element and you have a polar bond, so you have a dipole moment, and the dipole-dipole interactions will cause the boiling point to be higher than in the case of non-polar. Okay? All right, now, London dispersion is induced temporary dipole. All that means is that for whatever reason, the electron cloud shifts and it goes towards one side more than the other. And because of that, it causes a partial charge that is again temporary. So in a dipole where you have a polar bond, it's not temporary because it's always a polar bond. This is in the case of a non-polar bond. The electrons shift and cause a dipole, but it's induced and it's temporary. Okay, so it will have this momentary dipole moment, okay, where you have these partial charges, so you'll have some attraction, but then it's not really long-lived. The more elements you have within the compound, like when we looked at propane, there was a lot of carbons, a lot of hydrogens, right? So you have more chances of these induced temporary dipoles within a larger compound compared to a smaller one. Okay? So, London dispersion forces are attractions between instantaneous dipole and induced dipole. So again, temporary dipole moments that happen just because the electron cloud shifts to one side or the other, and it causes a momentary dipole that's going to disappear. It's going to go back to normal. It's not long lived. Okay? Questions? Great. So the tendency of the electron cloud to distort is called polarizability. The larger the compound is, the greater the polarizability. The greater the polarizability, the greater the London dispersion forces. The greater the London dispersion forces, usually higher the boiling point is. So you get a lot of questions on that kind of stuff where it asks you to justify boiling point and melting point and some other kind of property that has to do with intermolecular forces. And if you're comparing a nonpolar to a nonpolar, then you have to look for this term polarizability, meaning you have to look to see if you have more elements, more bonds, more polarizable it is. Okay? So polarizability is important to understand. The shape also affects the strength of the dispersion forces. So why does it do that? Well, the longer ones, and the straight molecules tend to have stronger dispersion forces because of the increased surface area. So these round ones, right? The round ones are less polarizable because of the fact that I have less surface area. So the greater the surface area, the greater the polarizability. Because both of those are pentane, so both of them actually have carbon. What that is. 21. Good.